All right, this is the video to finish up our 10B notes. I'm going to just have 4 examples to get through here. And we'll start with the last one on the penultimate page of the notes document, page 13. We have yet another power series whose interval of convergence we're interested in finding. You can kind of already see what's going to happen here. This one plays out a little bit differently than the first 2 examples from in class. But the opening step is the same. You can see this initial ratio test set up with the a sub n plus 1 times the reciprocal of the a sub n. As soon as we write it out, we're thinking about collecting like terms in the interest of simplifying. The x to a power terms are going to work out in a straightforward manner. Same with 5 to a power. All this gobbledygook with n we might need to talk through. You can see what I've circled here and rewritten a little bit down below. I've got it as n to the n, and then I've peeled off one of the n plus 1s in the bottom. Reason being, this n to the n from the original series leads to an interesting n plus 1 term. We don't exactly have the same exponent on these polynomials. By peeling a copy off, I can get the same exponent elsewhere for the sake of combining. So I'm turning all of this stuff into 1 over n plus 1 times n over n plus 1 to the n, which I've put up into our next line of work here. Now, the n over n plus 1 to the n is a bit tricky. There is certainly a way to sift through that with L'Hopital's rule, but in an effort to avoid showing L'Hopital's work today, I'm going with an alternate strat. I don't expect that you would come up with this strat on your own. It's kind of a unique, novel approach. It's not something you would ever have to do on a test or even the AP exam, so please don't worry about this too much. In fact, I think this problem as a whole is a bit extra and maybe is perhaps the difficulty level you have to worry about on a test. But what I'm choosing to do here with my n over n plus 1 to the n is consider that the reciprocal of n over n plus 1 could be rewritten as 1 plus 1 over n. And then recognizing earlier in the course, we saw a very special limit of 1 plus 1 over n to the n is equal to e, which means what we're dealing with up here, raised to the n, is actually equivalent to 1 over e. Again, I don't expect you would have noticed that, but I can then make a substitution. I can say that this entire portion becomes 1 over e. Meanwhile, the 1 over n plus 1 that I peeled off is perhaps the more powerful component of this all because it goes to 0, which means at the end of the day, my entire result that pops out of ratio test is just 0. It doesn't even matter what x was. No matter what you plug in for x, you're going to end up with this 0 popping up at the end, meaning your ratio test result is always less than 1. And therefore, we've stumbled into an example that has a interval of convergence of all reals. So that's the end of this problem. And we will move on to the next page. All right, what is the best way to figure out some space here? Move a couple of these boxes around. All right, I'm looking at the problem at the top here. All the work is written out already for these problems, so you might consider pausing the video and copying down work if you like. I don't necessarily feel the need to talk through every last step in great detail. But with this first one, I'll just point out just below the original series, we've got our ratio test set up. Things here are going to cancel quite nicely for us. These polynomials have the same overall degree top and bottom. Those will all go to 1, leaving us with just absolute value of x plus 3 being less than 1, leading us to the beginnings of an interval from -4 to -2. Notice the center is in fact -3, the radius is 1. We just need now to check the -4 and the -2. Over on this right panel here, I've got both of those checks. When x is -4, we end up with an alternating series. So I've shown the 3 steps for that, and I've got convergence at -4. When x is -2, we end up with something equivalent to 1 over n squared plus 2n, which looks remarkably similar to 1 over n squared. I've chosen to show the steps of limit comparison, but you could also have done a direct comparison there. We do end up with this non-zero result out of limit comparison. I'm noticing I forgot to write my little mini conclusion right here about 1 over n squared. So make sure to tell me right here where the hand is that it is a p-series, p equals 2, 2 is greater than 1. Okay. So yeah, here's my final answer. And we will move on down to the next problem, which is perhaps the most intense on this page. I'm going to start over on the left side. Here is your initial ratio test offering. Very carefully packaging up similar terms top and bottom to get some simplification in the next line of work. You would, unfortunately, probably have to show a L'Hopital justification to get further with this thing. But at the end of the day, we are going to get pieces that both approach 1 and therefore kind of disappear themselves out of the problem entirely, eventually leading us to absolute value of x plus 2 less than 1. So I know that I'm centered at -2. I've got my radius of 1. I'm looking at -3 to -1, and I need to check the bounds. I'll talk about the -1 first, just because the work is right here and it's quick and it's easy. If I plug a -1 into this original series, this portion where I'm highlighting right now becomes 1 to the n, which is effectively just 1, which effectively disappears. So I do end up with a much simpler alternating series where we can easily apply our alternating series test. I've shown the 1, the 2, the 3 steps here to get convergence at my -1. Now we go to check x equals -3. This is interesting. If I put a -3 in for x up here, I get yet another copy of -1 to the n. So now I have -1 to the n times another -1 to the n, which is really -1 to the 2n. If -1 is getting raised to an even power, it actually becomes 1. So all the negative stuff in the numerator just becomes 1. So here now in orange, I've got the updated version of the series. This is one that perhaps is challenging to confirm with a lot of our procedures. It actually does work well with integral tests. So I'm going to take this as an opportunity to demonstrate integral test one more time. Let me see if I can zoom in even a bit more. This orange font color. Whoop, there we go. All right, anyhow, let's remember first step, show me a function of x, not an integral, not a series, just a function. Tell me that it's positive, continuous, and decreasing as x gets big. Once we've got that established, we can dig into an improper integral. I would be fine if you start at the second step. If you want to bring in the limit and the b right away, I'm okay with that. As messy as this thing appears to be, it's actually quite a simple u sub, because we've got a log of an x plus 1 whose derivative is 1 over x plus 1 dx. So yeah, the dx with the x plus 1 in the bottom, that's the entirety of your du. This extra log just becomes u itself. So this integrand becomes 1 over u du. Couldn't ask for anything simpler. I do have to adjust the bounds. Okay. From there, I've got my antiderivative. From there, I'm replacing u with each of the bounds plugged in. And I see log of log, which, let's not be scared of that. It's an extremely slow growing function, but it does still grow infinitely. So just this first term here, as b gets bigger, 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 this first term goes to infinity. The second term being a constant, I don't really care too much about it. So my result is infinity. So integral is divergent. Our series is also divergent. And all of that work just to say we don't want to include -3 in our interval. And there you have it. Okay. Zoom this back out just a minute. One last little problem at the bottom. Don't worry, this is quick. It's just a little throw-in. It's not a full interval of convergence. Just a reminder that we really do want to see an absolute value of just x by itself, plus or minus a constant. We don't want any multipliers on x, otherwise we can't be guaranteed that the other numbers we see are the center and the radius that we want. So what I'm doing here is just showing you how to manipulate a slightly more complicated result out of a ratio test. If there's a 2 hanging out or any constant, we can move it to the other side with multiplication. If I do have a multiplier on x, I can factor it out. If I pull a 4 out of my absolute value, I now have x plus 1/4. The 4 moves over to the other side. So I see that actually the center is -1/4. The radius is 1/2 coming off of a result like this one. All right, that concludes the chapter 10b notes. Let me know if you have any questions. You can email me if you like, or ask me questions in class next week. Thank you for watching.